Hello students, today we're going to be working on determinants and inverse matrices. So last time we introduced matrices and operations and learned how we can use matrices to solve and manipulate the system of equations. Okay, today we're going to be continuing that topic, but with a more sophisticated tool. So let's go ahead and take determinant. So the determinant is defined the following way. The definition of determinant. So let's say the determinant of a matrix, 2 by 2 matrix, right, is given by the determinant of A, or absolute value of A, or this is also notation, is equal to A1 times B2 minus A2 times B1. So essentially A1 times B2 minus A2 times B1. Okay, and the determinant is have a lot of geometrical representation. Okay, so geometrically we can find the area of the parallelogram if we let vectors to be a1 b1 a2 b2. Right, this is more of a geometry topic, but essentially I'm not going to be drawing it, but if we have something like this, we can define it, this shape, this quadrilateral, as a matrix, right, with the coordinate points. Right, and this coordinate point, so directions of it, forming it as a matrix, will give us this exact area of this quadrilateral. So that's why it's very useful. In addition to it, we also can use it to find area of triangles, which we'll later on learn as well. Okay, so for now, we need to know that this is the determinant. And we're using the coefficient matrix specifically, right? This is not an augmented matrix. This is the matrix of coefficients. And this is specifically for a 2 by 2 matrix. Okay, so let's go ahead and take a look at some examples. So example 1, we will have, let A to be 2, -3, 1, 2. Okay, so then we want to go ahead and use the formula to find the determinant. So then the determinant of A is going to be, so 2, -3, 1, 2. So it's going to be 2 times 2, 2 times 2, minus -3 times 1. So we will have 4 plus 7 is equal to, 4 plus 3 is equal to 7. So, okay, how about this matrix right here? So how about B equals to 2, 1, 4, 2? What's going to happen here? The determinant of B is equal to 2, 1, 2. Is equal to, so 2 times 2, that is 4. 4 times 1, this is 4. So 4 minus 4 is going to be 0. So what kind of matrix B? We call it a singular matrix. So B, singular matrix. So that means that the determinant of that matrix is equal to 0. And that's going to be a very, very important property that we will be using for the inverses of the matrix. Okay, perfect. So now, well, 2 by 2 is nice, but most of the time we're dealing with the higher dimensional systems. So for the higher dimensional systems, we have to use two new concepts which are related to determinants, and those are going to be minors and cofactors of matrix, of a square. So we always talk about square matrix for this concept. Right, it's going to be a n by n matrix of. Okay, so let's go ahead and take the definition. Right, take a look at the definition of the minor cofactor. So if we have a matrix A and we want to obtain the minor, which we write as m I sub ij, of an entry A sub ij is the determinant, right, of the matrix obtained by deleting the ith row and jth column of A. And the cofactor Cij of the entry Aij is as following. Okay, so let's go ahead and take a look at an example. So example 2. So we will have A to be equal to 0, 2, 1, 3, -1, 2, 4, 0, 1. Okay, let's find minors for this matrix. So the minor of M sub 1, 1 for this matrix would be the following. So we have to delete the first row and the first column. So let's take a look. So 0, 2, 1, 3, negative 1, 2, 4, 0, 1. Right, so we're taking away the first row and the first column. Okay, and so our M11 is going to be the determinant of negative 1, 2, 0, 1, which is going to be equal to negative 1 times 1 minus 2 times 0, which is equal to negative 1. So now let's do M12. So what will be M12? So we have to delete the first row, second column. Negative 1, 4, 0, 1. Okay. So we're going to have to remove first row, second column. Our minor 2 will be 3, 2, 4, 1. Equal to 3 times 1 minus 4 times 2 will be equal to negative 5. Okay. And the cofactor, right? Let's take a look again. The definition of cofactor is the minor multiplied by negative 1 to the power of row plus column. Okay, so why do we need a cofactor? So a cofactor, and the layout of a cofactor is going to be the following. So it's a pattern of the signs in A. So here it is. If we have a 3 by 3, we have a 4 by 4, and by n in general. That's going to be the pattern of signs, so specifically for negative 1 to the power of I plus j. Right, we can check that by plugging it in. Okay, so why do we need a cofactor? So a cofactor is essentially helping us to reduce big matrices, such as a 3 by 3 or 4 by 4, into smaller matrices and find the determinants. So if a square matrix A of a dimension 2 by 2 or greater, then the determinant of A is the sum of the entries in any row or column of A multiplied by their respective cofactors. For example, expanding along the first row yields to A11 C11 plus A12 C12 dot 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 A of 1 n times C. So we can apply this definition to find the determinant, and it's called the expanding by cofactors. Okay, so that's why we can verify it by using the 2 by 2. So we know that it's just the cofactor itself, which would be we just learned recently. But let's take a look at 3 by 3 matrix. So if we have matrix A to be 0, 2, 1, 3, negative 1, 2, 4, 0, 1. Right, so we can expand it in a different ways. So we can do first row or first column or second row or second column, but it has to be in columns, right, or rows. So okay, but let's go ahead and do the first row. So we know this is going to be the signs of the cofactors, right, and we're going to use the values. So we're expanding across the first row. So then the determinant of A is going to be, so we're starting with the first part is going to be the 0, right? So we're going to have 0 times negative 1, 2, 0, 1. Positive, right? Because our sign is positive. Then the second one is negative. So it's going to be negative. And then we have first row, second column. So, and it's positive 2, right? So we're still going to keep the minus. So it's going to be 2 times 3, 4, 2, 1. Okay. And then the last one is supposed to be a plus. Right, a plus of the third row. So we're going to cross out the first row and the third column. So first row, third column, because we're expanding only across the first row. Okay, so we're going to have plus 3 plus 1 times 3, negative 1, 4, 0. Okay, now we're computing essentially a 2 by 2 determinant, right, which is much easier than a 3 by 3. So, and same thing would be a 4 by 4, we would reduce it to a 3 by 3, and then from 3 by 3, we'll reduce it to 2 by 2. Okay, so for A, we're going to have, so the first one is 0, right? So 0 minus, so minus 2 times, so 3 times 1 is 3, minus 8, that's negative 5, plus 1 times 3 times 0 is 0, minus negative 4, so that's plus 4. So we're going to have 10 plus 4, which is equal to 14. So the determinant for the 3 by 3 matrix is 14. Perfect. So we can do same thing for the 4 by 4 and etc. And we can also use a triangle rule. So a triangle rule. So let's try to do this. So if we have matrix A, and I'm gonna go write down general. So A11, A12, A13, A21, A22, A23, A31, A32, A3. So the triangle rule of matrices is the following. So we're multiplying this diagonal, or actually, even easier. So once we have a matrix, we can first write down the first two columns. So here, A11, A21, A31, A12, A22, A2. And now we can actually perform some math. So we're going to add this. So we're going to multiply A11, A22, A33 plus A12, A23, A31 plus A13, A21, A32. Right? So determinant of A here. Actually, I'm going to. So determinant of A is going to be A11 times A22 times A33 plus A12 times A23 times A31 plus A13 times A21 times A32. And then we're going to do the minus. So it's going to be minus. So we're going to do this. A31 times A22 times A13, A32 times A23 times A11, A33 times A21 times A. We're going to have minus A31, 22, A13, minus A32, A23, A11, minus A33, A21, A12. That's the general formula. Right, the reason why I wrote it down, most of the time when we have a matrix, it's much more easier because you might have some zero entries, or it's going to be just a lot of ones and twos, so it's very simple mental math to compute the determinant of a 3 by 3 matrix. And most of the systems that we're dealing with are going to be either 2 by 2 or a 3 by 3. Right, maybe we'll have a 4 by 4, right, in the rare occasions. Okay, now, since we learned how to do the determinants, we can go ahead and move on to definition of inverse of a matrix. So inverse of a matrix. So specific inverse of matrix, we're going to be focusing on matrix. So, but let's take a look at the proper definition. So, of course, we'll let A to be n by n matrix, and let In, which is the identity matrix, which we learned last time, be the n identity matrix. So if there exists an A power of -1, which means an inverse, right, an inverse, such that A times A inverse is going to be the unit net matrix, and it's the same thing. So the inverse is commutative, right? We can say A times inverse A is the same thing as inverse A times A, right? It should be commutative both ways. So then A inverse is the inverse of A, right? So the symbol, we read it as A inverse. Okay, so and sometimes we can, let's check it, right? Let's check through an example. So we can have something like, example 3. Let's say A is going to be -1, 2, 1, and then B is going to be 1, 1, -1. So A times B is going to be equal to, so remember the rules. So we're multiplying the first row times the first column. So we're going to have -1 plus 2, then first row, second column, it's going to be 2 minus 2. Then second row, first column, it's going to be -1 plus 1, and then second row, second column, that's going to be -1. That's equal to 1, 0, 0, 1. Okay, so that is indeed I2, right? This is the unit matrix here. So our identity matrix. So okay, now well, let's check that it's actually true. Then BA also should be an identity matrix. So let's check. So we multiply now B times A. So we're using the rows of B times columns of A for this case, right? So here we would have 1, -2, 1, -1 times -1, 2, -1, 1, right? This is a little different. So we're gonna have slightly different computations. Will we? No, we're gonna have almost exactly the same. So -1 plus 2, 2 minus 2, -1 plus 1, and 2 minus 1. So once again, we're getting 1, 0, 0, 1, which is our identity matrix in the 2 dimensions. Perfect. So okay, but how do we actually find the inverse of a matrix? And so in order for us to find the inverse of a matrix, we need to follow some steps, right? We can do it either through using the identity matrix, right, as a part of our steps. So let A be the n by n matrix, and we were right n times 2n matrix that consists of a given matrix A on the left and the n by n identity matrix right. So we want to obtain the inverse. So here, the easiest way is to imagine the following. So if we have a matrix, let's say we have a matrix A to be 1, 4, -1, and -3. We want to find the inverse. Well, we can set it up as the following. So we can set it up as 1, 4, -1, -3 / 1, 0, 0, 1. And so our goal is to perform the row operations such that now we move the identity matrix, right? Because the right-hand side here is actually the identity matrix, right? This is the identity matrix. So we want to make sure we can move it by using the rows operations to the left. Okay, so what can we do here is, okay, let's take a look. The first step here is for us, let's add row 1 plus row 2, change row 2. Okay, so we're going to have 1, 4, 1, 0, and then we add it to the second row, so we're going to get 0, 1, right? And then we have 1, 1. Okay, then the next step is for us to get rid of a 4. So we're going to have, well, let's do -4 times row 2 plus row 1, change row 1. So what are we going to have here? We're going to have 1, 0, 0, 1. But here we will have -3, -4, 1, 1. So our A inverse is actually -3, -4, 1, 1. And so this is a general way of finding size square matrix inverse, right? You can always do that. You have to match the dimension of the matrix. So 3 by 3, this is the most convenient way of finding it. However, we can use a formula for the inverse of a 2 by 2 matrix. Okay, so the inverse of a 2 by 2 matrix is related to the determinant. And determinant essentially defines if we can have an inverse in general. Because for the A of a 2 by 2, right, if we have it as A, B, C, right, then A inverse is going to be 1 over determinant times. So it's going to be, we're flipping D and A, so it's going to be D, A, and we're flipping the sign of B and C, so it's going to be -B, -C. Right, so the full format here is A inverse of a 2 by 2 is going to be 1 over A times D minus B times C multiplied, so this is a coefficient, right, multiplied by D, -B, -C. Okay, so when a matrix is singular, means that the determinant is equal to 0, then we do not have an inverse. So this is a very important part. So determinant of A must not be equal to 0 in order for us to have an inverse. Okay, but why is it important for us to learn the matrices? Well, remember how we did the augmented matrices last time to find the x, y, and z values? Well, now it becomes super easy for us because we know how to use matrices. So essentially, here is the rule. So if A is an invertible matrix, right, meaning that the determinant is not equal to 0, right, this is what it means invertible. We can invert it, find the inverse. Then the system of linear equations represented by A times x, so x here is essentially x, y, right? and b is the values, has a unique solution given by this equation. Okay, so let's take a look at an example, right? An example. So we might have something like a system like this. So if we have 2x plus 3y equal to 1, and negative x minus y is equal to 3, our system, we can rewrite it. How can we rewrite it? So our coefficient matrix, we write it as ax equals to b. So what's our a? Our a is 2, 3, negative 1, negative 1. Our x essentially is x, y. And it is our 2 by 1 matrix, and that's equal to 1, 3. So in order for us to solve it, we need to find an inverse, right? So a is equal to 2, 3, negative 1, negative 1. So a inverse, we can use the formula that we just learned. So what's our determinant? 2 times negative 1, so negative 2, minus 3 times negative 1, so minus 3. And then we're going to have negative 1, negative 3, 1, 2. Okay, so our determinant here is actually equal to 1. So our inverse, so it's 1 over 1, which is 1. So our inverse is negative 1, negative 3, 1, 2. Okay, and so we have to rewrite our equation, right? So that means our xy is actually equal to the inverse, which is negative 1, negative 3, 1, 2, times 1, 3. Okay, so if we multiply that, right, this is a simple multiplication here. So we're going to have negative 1 times 1, negative 1. Negative 3 times 3, that's minus 9. Okay, and then the second one is 1 times 1, that's 1, plus 6. So our x should be negative 10, our y should be 7. Right, and of course, let's go ahead and check it. So negative 10, negative 10 minus 7, so it's going to be positive 10 minus 7, which is 3. That works. And negative 10, that's negative 20, plus 21, that's going to be 1. So perfect, this is our x and y. Right. Next time, we're going to learn about partial fraction decompositions, and we will move on to sequences and series. See you guys next lesson.